Well, this video will discuss active galaxies and especially quasars, very luminous objects that the late 1950s, 1960s came to be observed and better understood as time went on. So some of their characteristics listed here on this slide. Um, After the distance was worked out, measuring the apparent brightness at Earth, and knowing that distance, their luminosity could be calculated, and they're found to be extremely luminous. 100 times the luminosity of a galaxy, 1,000 times, and not just emitting energy in the visible, but emitting energy in some of them in the radio spectrum, ultraviolet, gamma, um, not restricted to the visible the way that stars are. And spectra of these objects do not match a black body spectrum. They're different than a black body spectrum, telling astronomers the source of energy is not just a collection of stars. Stars have a black body spectrum. The light coming from these active objects is different than a black body. We're not looking at light from stars. The spectra have very strong emission lines, and these emission lines give evidence that there's a large redshift. A large redshift. So the emission lines tells us a very energetic process is occurring, high temperatures, and the large redshift is related to a very distant object. Also, the energy coming from the quasars is variable. On the order of a week, a month, the object can get brighter or dimmer. It's not a steady source the way a star is. So that's some of the characteristics. The quasars first found with radio detection, but then astronomers are able to narrow down the source on the sky and associate with some of these visible light sources. So here is 4C 71.07. In between the hash marks, the vertical hash marks here, you can see that object. I said that these were very luminous. Why is it that this is barely visible on this slide? Well, because it's very far away. It's much further than anything else on this slide, much further away. And it is truly luminous, giving off a lot of energy. But to us, it's dim because of the great distance involved. This large distance, even though so we can see them, the reason we can see them is putting out a lot of energy. And it may be that some of the reason we can see these quasars is the energy is not going out in a sphere the way that starlight energy goes out from the sun or some other star, but instead something like the pulsars, where you have the north and south poles and the rotation occurring. You have the electromagnetic waves somewhat beamed from the object. So this could be the case for the quasars as well, that we're getting the energy kind of directed rather than being sent out in all directions. This, of course, would make the quasar seem brighter and wouldn't need as big of energy source here to create the brightness that's observed. So this still to be explored, but we may have this situation. And that also means that we're not detecting all the quasars. If this beam of energy doesn't point towards the Earth, then the energy that comes out this way, it's not going to be enough to be visible at these large distances. So where are the quasars located? Now, as I said, they have a very large redshift. That tells us that it's taken part in a great amount of recession velocity and is very distant from us. There's other evidence that the quasars are distant. So there's a galaxy here in the center, and then these four blobs of light, they all have the same spectrum, same emission lines with the same amount of redshift, and astronomers are confident that these four pieces of light here are the images caused by the gravitational bending of light, and these are actually light from one object that's more distant than this galaxy. Now the galaxy here, and you're not seeing it very clearly because it is very far away. The quasar is farther away, than this galaxy. As the light goes past the galaxy, the light from the quasar, the gravitational effects, the bending of space-time, cause a refocusing of the light, and we get these spots here. So quasar is more distant than that galaxy. Just another point of information that the quasars are very far away. This large redshift that's been observed, the shifting of the spectral lines, it's not due to some individual motion that the quasar has at high speed through space. Instead, it's sitting a great distance from us, and the recessional velocity is what's producing the redshift. Other examples here of quasars that have been, their light has been refocused by the mass of this galaxy cluster. So more distant than the cluster. So as astronomers look at these distant objects, distance relates to time in the past. The further away something is, we're going to be seeing that object more in the past. Objects that are close to the Milky Way are more our present time, and as we look at the light getting to us today, as the object is further from us, that light started a longer time ago. So as we look at objects further and further away, we're investigating the conditions of the universe at greater times into the past. And what astronomers find there is that the number of quasars increases as the distance increases. That's saying that the number of quasars, the percent of objects that are quasars, is greater more towards the beginning of the universe, more in the distant past, and the number of quasars is fewer today. There are no quasars near the Milky Way. These objects are far from us. They're objects of the past, and giving us a little indication that galaxies may have started as quasars. And later, as the quasar activity decreases, we get a situation of our present day where the galaxies are not that active, not emitting so much energy. It could be that the Milky Way used to be a quasar when it first formed. All right, size of quasars. As astronomers measure the energy coming from the quasar, it does change over time. And it's not a periodic change. It's not a pulsar type change. It's not an eclipsing binary type change. It's more random as to when it gets bright and when it gets dim. So we're not dealing with some periodic effect here. But observed brightness, weeks and months. What's that mean for the size of the object? Well, if some event happens in the quasar region that makes it give off more light, if it was a light year in size, the brightness variation would take a year to complete. When the material that's close to the Milky Way gets brighter, that light starts moving towards us. When the object's distant side, the side that's more distant from the Milky Way, emits more light at this same time, it's going to take a year for that light just to get to the edge of the quasar object and then continue its journey onto the Milky Way. So if the object is small enough, then this light change can take place and not get washed out, not get averaged out by light coming to us from more distant parts of the object. If the object is compact, then we can see more sudden changes in the brightness, and a week is a sudden time on the scale of stars, lifetimes and so forth. So if we have a small object, it can change brightness over the whole object within a week, and we receive that signal, that increase or decrease in energy that's put out. If the object is a light year in size, then we have energy coming all the way across the object. The side of the object that's close to us gets bright. The other parts of the object are getting bright. This part of the object that's far away from us, that light's going to take longer to get to us, and it'll kind of wash out any sudden change of that the object might have. So ask your instructor to explain it better than I just did. But the fact that the light brightness changes in a week or a month, that sets a size limit on the object. If the object takes a month to get bright, then the object is not any bigger than one light month, the distance light would travel in a month. If the object takes a week to change its brightness significantly, then the object is not any bigger than a light week. So this size puts it a little bit bigger than our solar system. That's not very large. It's not the whole size of a galaxy. The quasars, energy is not coming from an entire galaxy. The quasar energy is coming from a very small region inside a galaxy. Well, what could supply the great energy that's observed? 100 times the luminosity of a galaxy, that's a significant amount. There's not enough hydrogen fuel, and the mass that's lost in fusion creates energy, but it doesn't create enough energy to match the output of 100 galaxies in a small space, in the space the size of our solar system. What if we have some supernova chain reaction, supernova moving in this in a small vicinity and exploding? That would be variable. If one star explodes and then we wait a while till another star explodes. Well, the supernovas stay bright for a few weeks, and we can't see how they could continue to put out the energy of the quasars. The quasars were discovered in the 1950s. They're still shining with great luminosity today. It's variable luminosity. It goes up and down, but all the time it's great luminosity. And there's not a mechanism where the supernovae could provide energy for that long. What about mass falling into a black hole? That turns out to be a good way to obtain energy. Mass falling in a gravitational situation will release a lot of energy. More energy gets released than for fusion, for example. So this is the current model, that there's material falling into the black hole. Again, we have the accretion disk and so forth heating up and sending out energy, not from inside the black hole, but from the region outside the black hole where there's a high temperature environment, high density environment, and we get the production of these beams, the light. So what's kind of a rough outline of quasars in their life? Well, astronomers are confident that the black holes are crucial in the life of a quasar. So we have a black hole that forms, and there's a collection of gas and dust and stars in the vicinity of the black hole. And those objects are captured by the black hole. The black hole gets bigger. The black hole gets more powerful gravitationally and becomes a supermassive black hole. Material will fall into this supermassive black hole. The material around the event horizon will move into the black hole. And as it does so, it releases energy, and we get the observed brightness of the quasar. The black hole region where this energy is coming from is outside the event horizon, and it's going to emit less energy as the supply of mass sort of dries up. And stars will orbit this supermassive black hole, but they won't fall in. So once the black hole kind of cleans up the area around it, there's going to be less energy available, and the quasar will dim out. And perhaps now what this quasar, this active galaxy nucleus, will settle down, become less energetic, and over 10 billion years or so, the active galaxy is done with its active part of its life and becomes more of a regular galaxy. The black hole at the center no longer emitting great amounts of energy because it's cleaned out the mass of gas and dust and stars near the black hole. So that's a little speculation, but it's a reasonable outline for the life of the quasar. So active galaxies, we have these very bright objects. They're seen at great distances. They have a big redshift, and we believe that they are black holes where there's mass moving into the black hole. That releases energy. Outside the black hole, this energy can be emitted and beamed somewhat to Earth. The quasars are more distant than galaxies and clusters of galaxies. And we find as we look at these great distances, the percent of objects that are quasars is much, much higher than the percent of objects that are quasars, at the, let's say, the position of this galaxy. So apparently the quasars were active a long time ago. As we look far away, we're looking a long time ago. The quasars were active at the time today in the region where the Milky Way is. We don't have any quasars. They've consumed all their material, fuel, if you will, that's near the black hole. And by saying fuel, I don't want you to give the impression that there's any chemical burning reaction. I don't want you to give you the impression there are nuclear reactions responsible for the energy. The quasar's energy comes from mass falling into the black hole. So you ought to read some more on this, ask your instructor, and keep reading astronomynotes.com.